In this video, we're going to talk about the phenomenon known as refraction, which is what happens to light as it passes from one material into another. We're going to see that light, which usually travels in a straight line, bends when it passes into a new material. We'll talk about why that is, and we'll look at the basic equation of that, which is called Snell's law. It helps us predict how much light will bend. After that, we're going to talk about how we can use curved surfaces to kind of bend light to the exact places we want it to. And that's going to be useful for making things like lenses, which are the components of everything from microscopes to glasses to telescopes. We'll talk a little bit about all these things. I have pretty distinct childhood memories of being shocked by refraction. Things like this pen in a glass of water appearing to be broken, or your arm in a bathtub appearing to have like a broken arm. The bending of light at surfaces leads to some interesting effects, and it's worth taking some time to go through and look at those effects.
So here's a laser pointer shining at a piece of glass. There's a couple of interesting things that we can see. The first is that some of the laser light is going through the glass and going out the right side of the glass. Some of it is reflected off of the glass towards the left. This is basically what happens at surfaces. Some light gets reflected and some goes through, which is called refracted. It'd be interesting for us to take a look at the various angles. I'm going to stop the film and use a ruler to draw in marks on the paper where the various rays of light are. So what I've done is I've marked where the light left the laser pointer, and then I've marked the spot it made when it hit the glass and the spot it made when it left the glass. And I've connected those dots with straight lines. And as you can see, it's not one big line. The glass is definitely bending the light. If we had to describe what was happening, the easiest thing to do is to draw a perpendicular line, which we call the normal. And we can see that instead of continuing straight at the boundary, the light seemed to bend towards the normal. It bent down in this case. When it left, it bent away from the normal. It went back the other way. So there's something about boundaries that makes light change the direction it's going in. And the thing that happens as light switches media is that the speed of light seems to change. It moves faster in some places and slower in other places. Let's look at an analogy of something else that changes as it moves from one material into another. Light bends when it refracts through a boundary between two medium. And the best description I've ever heard of this came in a textbook by James Walker, who talked about a marching band marching on grass towards a pit of mud. So the way he described it was each marcher, while they're on the grass, in a time delta t, moves a distance delta dg for a change in distance of grass. So this person in delta t, this person, this person, this person, this person, they're all going to move in the first delta t the same distance, which will put them there. And the process is going to keep repeating. Nice orderly format. Until this first person starts to go into the mud. Now, because they're entering the mud, they're going to slow down. And that's a problem because instead of going the same distance they did before, delta dg, they're going to go a small amount, delta dm. And the problem is the other people will have advanced their normal amount. So this person only goes that far, but this person still does delta dg, as do all the other people. So we've continued to march into the mud, and it's actually bent the direction that the marching band is going. So that might be easiest to see if I highlight it. We could say that the original marchers, they were in a line going straight like that.
And these start looking a lot like the peaks and troughs of a wave. So we're nice and parallel while we're on the grass. But then look what happens to our poor marcher here. The line connecting them to their colleague has bent. And then as we continue to march through, that bending affects more and more and more people. So what we see here is that the waves which were initially headed in this direction have curved because part of the wave got stuck in the mud, whereas the other wave continued on unimpeded. And that means that if we were going to draw a ray representing the direction the light was going, or the marching band was going, it would have bent like that. And that's what we see. We see that light that's coming in at an angle like this gets bent more towards the perpendicular or normal to the surface. So that is attributed to part of the wave being slowed down by the new medium. And it's one of the reasons light bends at the surface.
So I suspect some of you are saying, what's this about different speeds of light? I thought there was a speed of light. And that's the speed of light in a vacuum, where there's no material for the light to interact with. That's the 300 million meters per second, or the 3 times 10 to the 8th meters per second we've talked about already. But in a material or a medium, light interacts with the matter, and that slows it down. That's the reason that the marching band analogy is a good one. As light enters a different material, its speed is going to change. And that's what makes the beam of light appear to change direction. So it's worth paying attention to how much light slows down in a different material. And the analogy for this, if we go back to the marching band, is how mucky the mud is. Is it just going to stick to them a little bit? Well, that's only going to slow the marchers down a little bit, and their line's only going to bend a little. If it's like quicksand or really gooey muck, that's going to bend their direction quite a bit. So we actually define the speed of light in a material by taking c, the speed of light in a vacuum, and dividing it by a number called the index of refraction, and that's how much light slows down in that material. In the case of air, the index of refraction is really close to 1, so the speed of light in air is pretty close to the speed of light in a vacuum. But we can see that that glass block we saw has an index of refraction of 1.5, and that means that the speed of light in there is not 3 times 10 to the 8th, but 3 times 10 to the 8th divided by 1.5, or 2 times 10 to the 8th. So only 200 million meters per second. So it's a pretty big difference. So that accounts for why the light bends when it hits that surface. It slows down significantly. But notice that as it leaves the glass, it bends away from the normal. In other words, the exact opposite process is occurring. And we can see that the exiting beam is actually parallel to the beam it entered at. Let's see how the marching band analogy explains that.
Now what's going to happen when they exit the mud, or when the laser beam exits the glass? Well, this one is going to speed up first. So instead of just going the smaller distance, they're going to go a larger distance, kind of like what they were going before. And as we've exited our mud puddle and we're starting to move faster, notice we're bending back towards our original direction, away from the perpendicular. And that these two lines are roughly parallel to each other. So as we enter a media that slows us down, we bend towards the perpendicular. As we enter a media where we speed back up, we bend away from it.
And that's exactly what we see in the glass. We bend towards the normal, towards the perpendicular on the way in as light slows down. We bend away from the normal, away from the perpendicular as light exits the glass and speeds up. So refraction definitely changes the direction light appears to be going when it crosses a boundary between two materials.
So obviously it would be nice to have a law that describes how light bends as it crosses boundaries. And this is the law. And you can see why we use this idea of index of refraction instead of just listing the speed of light in each material. It seems to be important for determining how much light bends at a boundary. This side has to do with one of the two materials light's in, this side has to do with the other. And the sines of the angles times the indexes of refraction will be equal. So we can use this to calculate. If we know one angle and we know the indexes of refraction, we can figure out the other angle. It tells us how much light bends. All right, so Snell's law gives us a way of playing around with angles and materials. We can use oil, we can use water, we can use glass, we can use different kinds of glasses. That's going to affect how much light bends. We can also change the angles that we send light in at. So let's play around with some of the stranger things you can see with Snell's law. And then we'll talk about how we deliberately bend light to make images. One thing that divers know is that if you look up at the surface of the water from underneath, you don't see the sky everywhere. In fact, the sky seems to be in this narrow circle, which is called Snell's window. And this US Navy photo demonstrates that really well. The reason the sky only exists in one circle has to do with the angles that we just talked about regarding how light speeds up and slows down at the surface. Let's look at a more controlled example of this. A pot of beans that I was cooking back in December. I was making red beans and rice one day, and you have to soak the beans for a while before that, so this is basically a giant casserole dish full of water with beans on the bottom. I dropped something on the ground, and when I looked up as I was standing up, I noticed the beautiful reflections of the beans on the top surface. What's curious about this is we only see the reflection of the beans from this angle. We don't see any of the spices up here. We just don't see through it all. So, like we saw earlier in this video, at any surface you expect reflection and refraction, but here we're only seeing the reflection. I started moving to more extreme angles. I balanced the bean pot on the edge of the counter. And from this angle, you could see that most of what we see from below is a reflection of the bottom surface of the beans, but there's this kind of circular anomaly starting to grow as I get to steeper and steeper angles underneath. And if you get to a very steep angle, you could see that it's actually the entire lid of the pot. So in that circle underneath, there's a compressed image of this entire dome of the lid. We still see some of the bottom outside that circle, but this is actually an image of the entire lid of the pot. So here's the explanation for what we're seeing. We are here, and light is coming from above to try to get to us. And we know that light basically is going to refract at the surface. According to Snell's law, as we go into a media that makes us go slower, we'll bend towards the perpendicular. What's the most extreme example of light from outside that can actually get to us? Well, it's light that's basically almost parallel to the surface. So I've got this, and here it is refracting and bending closer to the normal, and it's getting into our eye. You can see that this basically goes all the way to the horizon in either direction. And that's why we see the entire dome of the bean pot. But from our point of view, it's compressed into the circle that corresponds to where the light from the horizon refracts into the water and gets bent down towards our eyes. So that describes what we're seeing in this Navy photo. If this sailor were to surface and look in this direction, this would correspond to the horizon that way. If he looked in the other direction, this would be the horizon that way. This is the entire sky collapsed into this circle. Notice what you see outside the circle. In the bean pot, it's very clear. You see a reflection of the bottom. Here, the bottom is so deep, we're just not seeing it. So there's just darkness. So we call what we saw with the beans total internal reflection. In these locations here, all you could ever see is a reflection of the bottom surface, and none of the light from that surface is actually leaving and going up into the sky. It's all being reflected straight back at the viewer. We can use the idea of total internal reflection for some other interesting things, including data communication. Let's take a look at that. So this plastic rod that's bent in this shape really shows how powerful total internal reflection can be. We have the green laser pointer. It's shining in, and because it's at one of these wide angles, it's not refracting through the surface, just like the light coming from the beams in the bottom of the pot, it's bouncing off. And it bounces back and forth without a loss of light. We get into here, notice we don't see any light over here. It all continues through the tube and eventually ends up shining on the floor. So data could be sent into one end of the cable by flashing the light in a certain pattern of on, off, on, off, on, off. And none of that light is going to be lost along the way. You can route cables like this under streets, between cities, and all they are bundles of fibers, glass fibers. And you can see that none of the light being sent from the top of this photo is lost out the sides. It all, or almost all of it, gets transmitted to the end. So this is a really efficient way of sending data. We're going to change tacks now. We're going to look at how we can use Snell's law to deliberately bend light in ways that enable us to make images using lenses. This is helpful for things like cameras and telescopes and microscopes. So we can use Snell's law to send light in different directions by shining light on curved surfaces. And the easiest way to understand that is to imagine that a curved lens, like I've got drawn here, is a set of glass prisms. And unlike the one you saw with square sides, these have triangular shape and trapezoidal shapes. And if you look at what I've drawn here, just like before, light is coming in and bending towards the normal. And then it's exiting and bending away from the normal. But if you start to have different shapes, you can actually send each beam of light in a slightly different direction. And notice I've sent all of these beams of light so that they seem to converge on a single point, which is called the focal point. All of these prisms stacked together make what we call a lens. And here's what an actual lens can do. I've got parallel beams of light leaving here, hitting this lens, and they're all being sent together and converging on a place called a focal point. This is probably something that everyone who's ever used a magnifying glass to try to light paper on fire understands. The sunlight, which is from very far away, is a lot like these parallel beams of light, and a lens focuses it all to a single point. The effect is also reversible. Instead of just taking parallel beams of light and sending it to a focal point, if you had a light source at a focal point and those beams of light left it and hit the lens, they would actually be sent parallel. So lenses are very diverse, they're very complicated. I don't want to oversimplify things. Strictly speaking, the kind of lens we're talking about is called a converging lens because it makes that light converge. There are also diverging lenses which make the light spread out. So optics is a really fascinating field, and we're only going to really graze the surface here. But I think everybody knows the coolest thing lenses can do is make images. So we've got our candle here, and on the other side of the lens we've got this perfect, beautiful inverted image of the candle. Notice it's actually a different size than the candle too. So what's happening is beams of light are leaving the object, the candle, at all sorts of different angles, and they're being redirected by the lens. Now, there is an infinite number of beams of light leaving this point source, but we can figure out where the image is going to be just by looking at what happens to two of them. This red line represents a beam of light that leaves our candle, passes through the focal point on this side of the lens. When it gets to the lens, it's going to be bent in a direction parallel to the axis running through the lens. So that's the red one. What's going on with the black one? It leaves parallel to that axis. It's going to be bent through the focal point. So what we end up with is light that diverged from this point comes back together at this point. And that's why an image forms there. It's actually not just going to be these two rays. It's going to be all of the light that comes back together at this point. You could block one of these two rays and you'd still see the image. In fact, that's how both an old mechanical camera and our eyes control how much light gets in to be imaged. You can open up an aperture which lets light come in from throughout the whole lens, or you could close that aperture which limits light just coming in from a few angles. But in either case, you're still going to get the image. Our eyes do something similar, as the iris, which on my cat here is this green material.
As it opens or closes, it's going to block rays from different angles, but she's still going to be able to see regardless of how wide open or closed that aperture is. If you have the time, investigating the relationship between the object, its distance from the lens, the image and its distance from the lens, is a fun experiment to do. If you have any magnifying glass in your house, you can do this. In the classroom, we use lenses that have focal lengths such that you can typically fit lots of different object distances and image distances on a meter stick. In your house, you'll probably have to be a little more creative. What I would do is I'd find various lamps at certain distances from the wall.
So I'll start with this lamp and this wall. So I get an upside down image that's about the size of my hand. And you can see how far away my magnifying glass is from the wall. Let's look at a lamp that's much farther away. Whereas if I use this lamp and this wall, which are much farther apart, notice the image is still inverted, and notice it's a lot smaller. So the size of the image can change too. You may want to investigate these, and I think it's kind of fun to wander around the house with a magnifying glass and see where you can make images. If you do it in a pattern and control variables, you should be able to figure out the relationship between image distance, object distance, size of image.
So anyway, this is a pretty big object, and notice its image is pretty small. It really just depends where the light reconverges. This picture I think is interesting because it shows something else that's really cool about images. This image, because the light from the object has reconverged here, it can actually be the object for a second lens. So I can show you that in real life. This is an image of the lock screen of an old phone I had, and you can see it's projected onto this screen. If I take this screen out of the way, this lens here can then take that light which converges here and make an image here. We won't actually be able to see the first image while it's being projected into the second image, but basically the continuation of the light that's here will hit this lens and remake the image. And it's hard to see, but there it is on that screen right there. So you can use lenses in combination with each other to get all sorts of effects, bigger, smaller, and interestingly enough, you can use them to correct problems with the first image. So finally, I just wanted to mention that a lot of times we use lenses in combination with each other to achieve different optical effects. This diverging lens and this converging lens, notice they spread out the parallel beams of light. Another place we like to do that is in our eyes if our eyes don't work quite right. The way your eye is supposed to work is the lens is supposed to focus an image on the photosensitive part, which is called the retina. And you can focus different distances because the lens is flexible. It can bend and change its focal length. But if you need corrective optics, contact lenses or glasses, it's because your eye is naturally focusing things to the wrong place. So if you need glasses for distance, they typically have this sort of shape to the lenses, and that makes the image farther away so that it's actually on your retina. The opposite's true if you need glasses for reading. Your eye is focusing the image beyond where your retina is, so you need it to focus closer, and you use lenses with this shape to do that. I hope you feel like in this video you've learned about how light can bend when it hits surfaces. It does that because the speed of light changes in different materials, and we can predict the direction things are heading using Snell's law.